Assalamu alaikum. Welcome to lecture number 24 of Digital Signal Processing. In the last lecture, we have done with the numerical values of frequency domain representation of the provided signal with the help of fast Fourier transform. Now we are going to plot that signal, and we are assuming that the sampling frequency is already provided in the signal. This is the frequency at which the continuous time signal is being sampled to obtain the sample set which is provided to us in the question. So the magnitude spectrum is basically this, and we have omitted the phase values as we are talking about the magnitude spectrum. Now we are going to plot this. At x-axis we have to take k, and at y-axis we are taking magnitude of ck. As we have ended up with the 8 points, so we have to mark the 8 points on k, and we have to plot these points. So first point is 0, second point is 4, then 2, again 0, again 0, another 0 which is at 5, at 6 we have 2, and at 7 we have 4. So this is basically the spectrum of the provided signal. But if we look at this spectrum, we can actually provide ease in calculation to the processor, as we know that all these values are not the unique one. Some of these values are redundant. So what are those values, or what are the unique values? We have to see the values which comes under n by 2 plus 1. So as you can see, n is taken as 8 here, so n by 2 is 4, and 4 plus 1 is 5. So first 5 samples are the unique one, and the remaining samples are redundant or conjugate of the previous samples, or the mirror image of the previous sample. And due to this very mirroring property, we are getting this U-shape spectrum. This is not the actual, this spectrum is not actually providing us the complete information, but some of these values are redundant. And we can see that if n is equal to 8, then we have to consider only the first 5 samples, that is 1, 2, 3, 4 and 5. So we have to consider the values up till here, which is when k is equal to 4. So these are the range which actually FFT is giving to us, and as we know that the unique range is up till here. And another interesting thing we can do with this numerical, that if fs is provided to us, we can actually the transform this x-axis from k to actual frequency, which will be in hertz. How? Fs will be divided by n, so we will have 1000 or 1 kilohertz. So the spectral spacing or frequency resolution is 1 kilohertz, which means that the two spectral lines are separated by 1 kilohertz distance. So once we get to know the frequency resolution, we can multiply it with k to get the actual frequency on x-axis. So this is 0 hertz, this is 1 kilohertz, this is 2 kilohertz, this is 3 kilohertz, 4 and so on. So if we again apply a Nyquist criteria, so Nyquist criteria states that if sampling frequency is 8000, then we can only the unique frequency which can be reconstructed from that signal will be from 0 to fs by 2. So fs by 2 will be 4000 or 4 kilohertz, which is again the same results which we are actually marked previously. So I hope that the concept of FFT is discussed in much detail and you have understand all the concepts, as this topic is very interesting and its application is much wide. So I want you people to give more concentration on this FFT lectures, and if you find any question or query you can directly ask me by emailing me, or you can note it down to ask me in the live session, or just comment in the classroom, so I will give your answer. So in this way, the second part, which is the part B of our DSP course, which is frequency analysis of signal, is come to an end, and now we are proceeding to the third major part of our course, which is analysis and design of system. Up till here we have discussed about the signals and how we can analyze signal. You people are quite familiar with the techniques we can utilize to analyze any signal. By the term analyzing, now you understand that I want to actually say that which frequency components are present in that signal. So after knowing the frequency components, we can actually add or remove some components or process that signal in according to our need or desire, that to perform some specific task on that frequency domain view of that signal, and then again we can transform that frequency domain view into again time domain to get our desired results. So in the part B we learn the frequency analysis technique. Now we are moving towards the third part of our course, which is analysis and design of discrete time systems. Now in this part we will discuss and see how we can design a discrete time system, and if already designed system is available, how we can analyze it. By the term analysis means whether the system is stable or not, or what kind of output it will generate. So for this we actually have two approaches. First one is the time domain representation and the second one is frequency domain representation. We can analyze the system or design the system in time domain, or we can analyze it in by using the information based upon its frequency domain. One point I need to add here, that in discrete domain the term system and filters are interchangeably used. That means if I'm talking about digital filters or discrete time filters, then they are nothing but the discrete time systems, because systems and filter are both the same thing. They are used to process any discrete time signal. So in time domain we can represent our system by using the impulse response. We can represent the system by using the mathematical expression, which is its difference equation. And the third approach is by using the block diagram, which is the graphical representation. The third representation, which is block diagram representation, is already discussed in the initial lectures. You may remember we have studied the block diagram in terms of direct form 1 and direct form 2. So this is basically the graphical representation of any discrete time system. So in these lecture we will discuss impulse response and difference equation in much detail. Apart from the time domain representation, we can also analyze system in frequency domain. And the frequency domain representation means by using certain mathematical tools, just as we utilize to analyze signal, to transform signal from time domain to frequency domain, we can also apply some mathematical tool on the above given representation to convert them into frequency domain. And what are those tools? Those tools can be Fourier transform, Laplace transform, or Z transform. So with the help of these tools, we can actually transform our system from time domain to frequency domain. So we will choose what our application is, and according to application and need, we will judge which representation is more convenient to you. In general, frequency domain representation is much convenient to us because it provides more detailed information of any system or signal. So as we are discussing systems here, so we will study the techniques which are used to analyze any discrete time system, which may be Fourier transform, Laplace transform, or Z transform. And we will also see the relationship between these mathematical tools also, that which tool is better or where we are required to use these tools. However, there may be some pros and cons of each tool, so we will discuss it also, that which tool is better and in which terms. But before that, we will discuss the time domain representation, which is impulse response and difference equation. So the first time domain representation of any discrete time filter or digital filter is its impulse response. There are basically two techniques or two types of impulse response. First one is finite impulse response, and those filters which yields finite impulse response are termed as FIR filters. Another response is infinite impulse response, and those filters which produces infinite impulse response are termed as IIR filter. Let's discuss what is FIR and IIR. FIR is finite impulse response, as its name implies, are those systems whose impulse response exists for finite duration of time. I am repeating again, FIR systems are those systems whose impulse response exists for finite duration of time. Or in other words, in terms of causal system or non-causal systems, so FIR systems are those systems whose current output, which is the present output, does not depend upon the previous output samples. So both the definitions are valid. If you are talking in terms of impulse response, then FIR filter are those filters whose impulse response exists for finite duration of time. Or in terms of output, a system whose current output or present output does not depend upon previous output samples are termed as FIR filters. So what are IIR filters? IIR filter are those filters whose impulse response exists for infinite duration of time. As its name implies, they are infinite impulse response filters. So their impulse response exists for infinite duration of time. Or in other words, we can say a system whose current output depends upon previous output samples. So they are IIR filters. Or we can say that IIR filters have some feedback because their present output is depending upon the previous output sample, and previous output sample is fed back to the system as an input. So these systems, which are IIR system, are having some kind of feedback. So this type of feedback is basically utilized to make the system stable, because after getting the feedback we can take decision on the basis of feedback that what type of output do we need now. So IIR filters can be stable or can be stable depending upon the nature of feedback or depending upon the nature of arrangement of system. So in this way we can represent our system on the basis of FIR or IIR, and also on the basis of causal or non-causal. And what are causal and non-causal systems we have already studied in the initial lectures. And the third is the operation, which is low pass filter. So we can classify any system, or we can say any system as this is FIR based causal low pass filter, or we can say this is IIR based non-causal high pass filter or band pass filter. So we can classify system in terms of its qualities, such as this system is FIR based, this system is causal or non-causal, or which type of operation this system is performing, either low pass filter, either high pass filter, or either it is band pass filter. So we can qualitatively analyze system and name the system accordingly. However, we can tell the response or some of the properties regarding some specific system by looking at its difference equation. So we will see how we can inform or comment regarding the properties of any system by looking at its difference equation in the later slide. Second kind of time domain representation is by means of its difference equation. Difference equation is nothing but the mathematical relationship between discrete time input and output signal with some coefficients. We already discussed the standard notation of difference equation in the initial lectures where we have divided the difference equation in two parts. First one is recursive and the second one was non-recursive. So here is an example of a difference equation in which input and output variables, which are x of n and y of n respectively, are arranged and depending upon each other in a certain fashion. So this basically equation is representing a discrete time system. So by looking at this equation we can comment on various properties of system just by looking at this difference equation. First thing we can tell about by looking at this difference equation is the input and output sequence must be discrete, because here the x and y variable are depending upon n variable, which is representing discrete time system. So input and output sequence must be discrete. Another thing we can tell by looking at the difference equation is its nature. It is finite impulse response system. Just by looking at the difference equation we came to know that there is no feedback involved in the relationship, that is the current output is depending upon the current input as well as the previous input, and it is not depending upon the previous output, which is or which may be y of n. So if y of n is written here, then it is depending upon the previous output, but as you can see that the current output is only depending upon the current input sample and the previous input sample. So this system is basically FIR system, or we can say that this system is open loop system, that is this system is having no feedback. Another thing we can tell about by looking just at its equation is the order of filter. It is a first order system or first order filter. Basically filtering action, which are zeros and poles, are decided by frequency domain representation. But by looking at the difference equation we can tell the order of filter by looking at the maximum delay which this filter is providing us. So we can see the filter is maximum providing the one delay in its equation. So one delay means the order of the filter is first. So it is first order filter. Another thing we can tell about this system is its causality or non-causality. So this system is causal system. That is, it is delayed but it cannot be advanced because n minus 1 is used, neither n plus 1. So this system is a causal system. This system is a dynamic system. This system is basically a discrete time system, or this system is an FIR system, or this system is a open loop system, or this system is having no feedback, or the order of this filter or this system is first order. So all these information which I just told you is on the basis of by looking at its difference equation. We can tell more about the system by doing some special mathematical operation on these equation, and we also predict the impulse response of this system. So how amazing it is. We can tell the impulse response of the system by just applying certain mathematical operation on its difference equation. So how we can exactly find the impulse response, we will see it in the later slide. So I have used the same system represented by the same difference equation. Y of n is equal to x of n plus 0.9 of x of n minus 1, and it is asked to find the impulse response of this discrete time system. So as you all know that if we have a certain system, and as we are discussing discrete time system, so we consider this system as a discrete time system. So this system maybe have any kind of input, and according to that input it will yield certain output. So input can be termed as excitation function and the output can be termed as its response. So if we apply at impulse at the input side, what we will get? Impulse response. Because whenever we apply impulse at the input side of any system, whatever the output we will get, we term that output as impulse response. And usually impulse is denoted by sigma of n, as we already studied while we were discussing the standard functions, which are unit impulse function, unit ramp function, unit step function. So we studied there that standard impulse function is denoted by sigma of n or delta of n, and whenever we apply delta of n to any system, it will yield impulse response, which is denoted by h of n. So with the help of this information, we are going to find out the impulse response of this system by using the given difference equation. What we need to do? We just replacing the input by delta of n, and we are replacing the output, which is y of n, by h of n. As we already concluded that whenever impulse is applied to the system, it will yield impulse response. So this is the x of n, which is the input, and this is y of n, which is the output. So x of n is replaced by delta of n. See that I have replaced x of n with delta of n, and similarly x of n minus 1 is replaced by delta of n minus 1, and output y of n is replaced by h of n. So the equation become like this. Now look very carefully how we can calculate the impulse response from the given difference equation. As we converted the equation in our desired form, that is replacing xn with delta of n and yn with impulse response, which is denoted by h of n. Now we have to work on this transformed equation to determine the impulse response of this system. Actually, in this equation, we have to substitute different values for n, and for different values of n, we have to calculate the impulse response, and finally we will combine the values to get the total impulse response of that system. First of all, we put arbitrarily n is equal to -2. We can also start from n is equal to -3 or -4. But as we can see from the equation that input is displayed by only one unit, so it is feasible to start with -2. If the equation is delayed more, such as -3 or -4, then we can start with -5 or -6. So as we can see that the maximum possible delay in this equation is 1 unit delay, so we can start our calculation by considering n is equal to -2. By placing n is equal to -2 in the above equation, we will get this equation. Here n is replaced by -2, again delta of -2, and delta of n minus 1, which means delta of -2 minus 1. So we only replaced n with -2. By doing so, we are ended up with delta of -2 plus 0.9 delta of -3. Now recall the very important property of impulse function, which is impulse exists for time when n is equal to 0, because this is the speciality of this function that it exists only for n is equal to 0. For other values of n, this function is 0. By using that property of the impulse signal, we know that impulse function does not exist at -2. So we place 0 here, and we also know that delta of -3 is also equals to 0. So 0.9 multiplied by 0, we will get 0. So the impulse response at -2 will be 0. Now we will repeat the same procedure by considering n is equal to -1. When we place n is equal to -1, then our equation becomes like this. And after simplification, we will get this equation: delta of -1 plus 0.9 delta of -2. Again, by using the same property of unit impulse function, that it exists only for n is equal to 0, and for other values of n, this function is 0. So as you can see that here impulse is to be recorded for instant n is equal to -1, and here delta of -2, and at both these instants we know that impulse function is 0. So the overall result at h of -1 will be 0. So we are getting actually the impulse response at different instants. We already get impulse response at n is equal to -2 and at n is equal to -1. Now we are proceeding with different values of n. Here we put n is equal to 0, and by putting n is equal to 0, our function becomes h of 0 is equal to delta of 0 plus 0.9 delta of 0 minus 1. And after simplification, we get this function. And if you look at this function very carefully, then we know that the delta function at n is equal to -1 is 0. So 0.9 is multiplied with 0. But the important thing is you can see that delta of 0 is 1, Because we know that at time instant n is equal to 0, this function exists and its magnitude is 1. So we simply place sigma of 0 is equal to 1. So after simplifying, we will get impulse response at n is equal to 0 is equal to 1. Now we have to proceed further by different values of n. So we consider n is equal to 1 here, and by putting n is equal to 1, our equation becomes like this. And after simplifying the above equation, we will get this form. And in this form you can notice there are two time instant where we have to put the values of delta function. One is at n is equal to 0 and other is at n is equal to 1. Again we know that at n is equal to 1 impulse function remains 0, but for n is equal to 0 our function yields a value which is equal to 1. So 1 is multiplied by 0.9, so the final result will be 0.9. In the next step, we further increase the value of n by 1 unit, so n becomes 2. And after putting n is equal to 2 in the standard equation, our equation becomes like this. And after simplification, the equation becomes this. And if we put the values of impulse function at these time instants, which is sigma of 2 or delta of 1, then we know that at n is equal to 2 delta remains 0, and at n is equal to 1 delta remains 0. So the overall impulse response at n is equal to 2 will be 0. So we have to solve this numerical by using our theoretical understanding as well, and we have to intuitively analyze the situation by looking at the difference equation to choose the value of n. We have to choose the value of n, or we can say the range of n very smartly, because we know that the impulse function exists only at n is equal to 0. So we know that at n is equal to 0 we will get some answer or some magnitude, and because this function remains 0 for other values of n, we will return with no answer. So we have to choose the range of n very smartly to determine the overall impulse response. So you can see that if we further increase n is equal to 3, 4, 5 and so on, our function will become like this, so that the value of delta function remains 0. So we will get h of 3, h of 4, h of 5 and so on, all equal to 0. So we don't need to calculate at these value. So finally, concluding the results, the actual expression is given as follows, and by using the mathematical trick and mathematical operation, we actually calculated the impulse response with the help of this available difference equation. And the impulse response we are getting at two instants. First is at n is equal to 0 and the second is at n is equal to 1. So we represent it in terms of sequence, because impulse response is again a signal, so we represent it in the form of sequence. And you can see that we have placed arrow at the first value which is pointing n is equal to 0, and this is n is equal to 1, and we placed the result of n is equal to 0 as 1 here, and the result of n is equal to 1 which is 0.9 here. So in this way we are ended up with our desired answer, which is the impulse response of the given system. This impulse response is also backing up our statement which we stated earlier, that this system is FIR system, and FIR system are those systems which has finite impulse response. And you can see from the impulse response that impulse response exists for certain specific values of n. That is, it exists for infinite, not for infinite values but for finite values for of n. So in this way we can say this is FIR system, which is finite impulse response system, as its impulse response is calculated to be finite. Now we will see another example of IIR filter. So this is the question, which is again basically a difference equation, and we are going to calculate the impulse response from this equation. But before calculating the impulse response, we already know that this equation is for IIR system. That is the system which has infinite impulse response, because it involves feedback. And how feedback is involved? Because we can see in the expression, output is depending upon the previous output. So it means that some feedback is involved with this type of system. Again, we can prove it mathematically also, that this system is infinite impulse response system. By using the same strategy, we have to substitute the different values of n in the transformed equation, and equation is transformed in a similar way. Y is replaced by h of n and x is replaced by delta of n, which is the impulse function. But here you can notice that in the equation we have replaced x with delta of n and y with h of n. So we have to put the previous output value in the current output. For example, if we are considering n is equal to -2, then actually we have to put the value of impulse response at the previous time instant, which is the feedback value. And we know that impulse function exists for only at n is equal to 0. So there is no impulse function before. So the value before this time instant is 0. Because there is no impulse, so there is no impulse response. So in this way, impulse response at h is equal to -3 is 0. And again impulse function at -2 is again 0. So overall result or impulse response at h is equal to -2 is 0. Similarly, for n is equal to -1, we have two functions, delta of -1 which is 0 and impulse response at n is equal to -2, which is the result we obtained in the previous step. So here we get 0, we simply put 0 here, 0 multiplied by 0.9 plus 0 is again 0. So the impulse response at n is equal to -1 is again 0. Now for n is equal to 0, our equation simplified to this form, and we have to put the value of this and this. This value is obtained from the previous step, which is again 0. So 0 multiplied by 0.9 is 0, and we know that delta of 0 is 1, because this is the impulse function which exists at n is equal to 0 and its value is 1. So we placed 1 and finally we get h of 0 as 1. Now proceeding with the solution by considering n is equal to 1. After putting n is equal to 1, we will get delta of 1, which we know that it is equal to 0, and h of 0. So we have to look at the previous response, which is 1. So 0.9 multiplied by 1 is 0.9. Now for n is equal to 2, the impulse response used is for of previous step, which is 0.9. So this 0.9 is multiplied with the impulse response at time instant n is equal to 1, which is the result obtained in the previous step, which is again 0.9. So 0.9 multiplied by 0.9 is 0.81. And you can imagine, if we calculate it for n is equal to 3, it will again come as 0.9 multiplied by h of 2, and h of 2 is 0.81. So 0.9 will be multiplied with 0.81, so we will get 0.729, and this step repeats forever, and it will not converge to any point, but it will remain present for infinite values of n. However, this value is basically decreasing, but it remains there for infinite value of n. You can see here we have put the value of n is equal to 3 and we obtained 0.729, and you can imagine if we put the other values we will get the answers. So again, its impulse response is found to be infinite as it is not approaching to some constant value or zero value. So in general we can represent this set or this sequence in terms of 0.9n u of n. So this is the generic representation of this impulse response. So I hope that the concept is clear to you now, and you can easily now determine the impulse response of any system with the help of its difference equation.